Alright, hello class. So today we are going to talk about geometric series. And this is one of the few types of series that we can actually determine what it converges to, if it converges. So far that's only been telescoping series, and now geometric series are ones where we can actually evaluate and get a number out. So not just tell if it converges, but also get what it converges to. These are actually fairly nice for that reason, and geometric series are of this form here. You might not be able to tell what the pattern is just yet, but essentially a geometric series looks like this. It's the series k going from 0 to infinity of, say, r to the k. Okay, so you'll get r to the 0 plus r to the 1 plus r squared plus r cubed plus r to the 4th plus r to the 5th plus r to the 6th, so on and so forth. Okay, so in this particular example we have here, these are all powers of 2, or 1/2, sorry. This would be 1/2 to the 0, right, which would be 1, plus 1/2 to the 1, plus 1/2 squared, plus 1/2 cubed, plus 1/2 to the 4th, etc. And here are r, so let me write this, r is 1/2, and this one in pink, our r is 1/3. Alright, because this would be 1/3 to the 0, plus 1/3 to the 1, 1/3 cubed, or sorry, squared, plus 1/3 cubed, etc., on and on. Okay, so these are series that take basically some number raised to the k, and that's what we're adding up. So it'd be that base to the 0 plus that base to the 1 plus that base to the 2nd plus that base to the 3rd, and so on and so forth. Okay, and how we analyze geometric series, it's actually pretty clever, I think. What we're going to do is take a look at the partial sums. So consider, okay, let's consider the nth partial sum. All right, so that would be, say, Sn, which will be, when we do this, it will be r to the 0 plus r to the 1 plus r squared plus r cubed, all the way up to r to the n. Okay, so I'm going to simplify this a little bit to make it a little easier to work with. This will actually be 1 plus r squared plus r cubed, and then all the way up to r to the n. All right, now keep this in mind. We're going to come back to it, because now I'm going to look at, I'll do it in yellow, I'm going to multiply this by r. So I'm going to take r times Sn, so that would be each one of these times r. All right, so let me write it out like this. It'd be r times 1 plus r squared plus r cubed, all the way up to r to the n. So when we distribute that r across, we're going to get r, okay, plus r squared plus r cubed plus r to the 4th, all the way up to r to the n plus 1. All right. Okay, so now that I have this, I have just my normal Sn, and I have my r times Sn, and here's the clever part that I find pretty neat. I'm going to take Sn, and I'm going to subtract by r times Sn. Okay, so I'm going to write it like this. Your Sn, of course, is the 1 plus r squared plus r cubed. I'll go ahead and write another r to the 4th on up to plus r to the n. So there's our Sn. Now I'm going to subtract away this Rsn. I'm going to align it such that, because this one starts at r, so it's going to be minus r squared minus r cubed minus r to the 4th. So you see why I wrote another term out. Minus all the way up to minus r to the n minus r to the n plus 1. All right, so as hopefully you can see here, all these middle terms cancel away. So we'll get all these cancellations, and then we'll be left with just 1 and then minus r to the n plus 1. This is what I find so clever. So Sn minus r times Sn is equal to 1 minus r to the n plus 1. All right, now the next thing we're going to do here is on this side of the equation are the terms both share an Sn, so I'm going to factor that out to get Sn, and we'll have 1 minus r is equal to 1 minus r to the n plus 1. And now I'm going to divide both sides by this 1 minus r. Okay, so we end up with Sn is equal to 1 minus r to the n plus 1 all over 1 minus r. And here is the formula I'm going to use, okay, because remember the series, the full series, k going from 0 to infinity of r to the n, r to the k, remember is going to be the limit as capital N goes to infinity, and I could use the lowercase n here, it doesn't have to be the uppercase n. So the limit as n goes to infinity of Sn, but Sn we found was that, so this series will be the limit as n goes to infinity of 1 minus r to the n plus 1 all over 1 minus r. So let's take a closer look at this and see what this limit ends up going to. Okay, so essentially the n is only affecting this r to the n plus 1. Like this 1 isn't affected, this 1 minus r isn't affected, so it's really just this piece. All right, now what ends up happening here is r to the n plus 1. Well, this limit has a few things it can do, okay? Well, maybe not a few, it's really just a couple of things it can do. The obvious thing is if this r is, say, greater than 1, say if this is 2, that's going to go to infinity. Or if this r is, say, less than 1, like it's 1/2, it's going to go to 0. So imagine if we looked at it in a graph form, like r to the x. R to the x, well, if r is greater than 1, you'll get exponential growth. And if r is less than 1, you get exponential decay. And then you'll just get 1s if r is equal to 1. But in this case, so it can go to 1 if r is equal to 1. So it'll go to infinity if r is greater than 1, it will go to 1 if r is equal to 1, and it will go to 0 if r is less than 1. And that gives us a sense of where this is going. So if r is greater than 1, we're going to get this thing diverging. Okay, so this diverges or converges based on r. Okay, so let's clean this up a little bit, and I'll give you the actual property for geometric series. All right, so here's the main property. The geometric series, r to the k, it will diverge if the absolute value of r is greater than or equal to 1. So the reason we're using absolute values is because we could deal with negatives, right? These can alternate if we want it to, and we can still get convergence even if it does. Or it will converge to 1 over 1 minus r if the absolute value of r is strictly less than 1. So at equals 1, we also get divergence because 1 to the k will be 1, and you'll just be summing up 1s over and over again infinitely. Okay, so that is definitely divergence. All right, so just to give a quick example, and these are actually fairly straightforward, but excuse me, if we take a look at this series, k going from 0 to infinity of, let's say, 1/2 to the k. Well, 1/2 is less than 1, so r is 1/2, which is less than 1. So we know we get convergence. We get convergence to 1 over 1 minus r. All right, so when we simplify this, this is 1 over 2/2 minus 1/2, so 1/2, so we get 2. Interesting. So what this tells us is that series we started with at the beginning, the 1 plus 1/2 plus 1/4 plus 1/8, okay, plus 1/16, on and on, actually equals 2. All right, now that may seem kind of odd. I'll show you in a second where that comes from. All right, but that's really as simple as it gets with these. I'll show you how we can complicate these things in a little bit, but let's say I have k going from 0 to infinity of 1/3 to the k. Well, here our r is 1/3, which is less than 1. So that was the second series we considered. So this should converge to 1 over 1 minus 1/3. So that will be 1 over, well, 1 minus 1/3 is 2/3. So this will converge to 3/2. Okay, and it's, you know, that straightforward. I like geometric series because they're pretty easy to deal with. Let's say I have 1.1 raised to the k. Well, that, our r is 1.1, which is greater than 1, so this diverges. All right, so we don't have to do anything else past that. Okay, so let's see. Let's take a look at another one. All right, let's have the series let's put a negative. Okay, negative 1/2 to the k. Well, negative 1/2 to the k, that's going to be, it's going to oscillate. At 0, we'll still get 1, but then we'll get minus 1/2 plus 1/4, minus 1/8 plus 1/16, minus 1/32 plus 1/64, and so on. Okay, so that's why we introduced the absolute value, because r is negative 1/2, and the absolute value of r is 1/2, which is less than 1, so we get convergence. So this series here converges to 1 over 1 minus. Now, we don't put the absolute value of r in this formula. We still put the minus 1/2. Whoops. Of course, I say that and I don't actually do it. We put the minus 1/2 here in the denominator. Right? So we actually get 1 over 1 plus 1/2. So that's 1 over, sorry about that. It's 1 over 3/2. So this series converges to 2/3. All right. Now, that's less than what we got with the one up here with just 1/2. Right? For 1/2 as our r, we got 2. Here we got 2/3. Hopefully that makes sense because we're adding and subtracting. So we should get something smaller because we're subtracting every other term instead of adding every other term. All right, before we get much further with this, I wanted to give you a visual example kind of showing you how this works. So suppose we have a rectangle that is, say, a 2 Let me actually help myself out here. Let's say it's a 2 by 1 rectangle. Okay, whatever our units might be, maybe 2 feet. What happened? All right, so we know that the area of this rectangle is going to be 2. All right, so what I want to do is I actually want to start chopping this rectangle in half. So I want to chop this rectangle in half. So let's see if I can do that. I'm going to chop this rectangle in half and then take the area of this piece. So the half of this rectangle, which is a 2 by 1, should be a 1 by 1. So this area is 1. All right, and then I'm going to do this again. There are a lot of ways we could go about doing this, but I'm going to chop what's the remaining part in half. Let's do it this way. So we chop this piece now in half again and take this area. Well, this area is now a 1 by 1/2. Right, a 1 by 1/2, so this area is 1/2. All right, then I'll take the remaining piece and cut it in half and pick one of the sides. I'll pick the inner side here. All right, and I'll find this area. Well, now this is a 1/2 by 1/2 rectangle. That should have an area of 1/4. Okay, and then I'll continue this pattern. I'll cut what's remaining here in half. All right, and so this, okay, so this is already a length of 1/2. So this is a length of 1/4 by 1/2. So this area will be 1/8. And then I will cut this, what's the remaining bit, in half again. Okay, so what we'll have now is a 1/4 by 1/4, which is 1/16. All right, then we'll cut it in half again. And hopefully you can start to see what's happening here. So we will get... All right, and then this next piece will be a 4th times an 8th, which will be 1/32. And then the next piece will be a 64th. And if we just continue doing this, hopefully you see that as I keep chopping this rectangle in half, that eventually I'm going to fill in this rectangle. Now, it will take me forever because I could zoom in right into here, and, you know, of course, my computer doesn't do a great job of that, right? But I can continue cutting in half, cutting in half, cutting in half, and continue to zoom in. Okay. But eventually, these pieces eventually approach the total area of the entire thing, which is 2. Well, this rectangle represents our geometric series of 1/2 to the k, which we found actually approaches 2. So here we have graphically a way that verifies this for us, okay? And we had a way mathematically that verified it for us. So this hopefully, I hope, shows that we can actually sum up a bunch of things, an infinite number of things, and actually approach a number, because we will never leave the rectangle the way we were doing that, but we could continue to zoom in, right? We could zoom in so close that the rectangle left, the empty rectangle, looked like this, and then we would continue the process again, except this one would be like 1 over, say, 1024 or something like that. And then you would continue down and then zoom in again and continue down. But eventually, when it's all said and done, we know that we're filling up this entire rectangle, and the area of the entire rectangle is 2. All right, so hopefully that helps convince you that there is something going on here. And I like that this is a geometric example to show maybe why it's called a geometric series. Okay, so we will look at a couple more examples, but this is really it in a nutshell. Okay, what I'm going to show now are just some of the ways we can complicate this idea and how we could use this even if it doesn't fall under our exact series. Okay, so for this particular example, I want to see if this series, k going from 2 to infinity, of negative 0.15 raised to the k, converges or diverges. Now, our r is negative 0.15, so our absolute value of r will be 0.15, which is less than 1, so we know we'll get convergence. Okay, the only problem is, and I'm curious if you caught it, our problem is our starting point. That formula we have is only valid when our starting point is 0. When our starting point's not 0, what we have to do is sort of adjust, kind of adjust what we're doing. So there are a couple ways we could go about doing this. So notice that if we had 0 to infinity of negative 0.15 raised to the k, well, that we know from just our formula that we'd get 1 over 1 minus negative 0.15. Okay, so we'd get 1 over 1.15, and you know, we could figure out what that is. Maybe use our calculator to see that 1 divided by 1.15 is, oh, well, it doesn't come out to be anything very nice. So I'll just say it's approximately 0.87-ish. Okay, but notice that we are starting at 2. So what I would say is here, so this 0.87, that's approximately starting at 0, so that would be 1, then minus 0.15, okay, plus 0.15 squared minus 0.15 cubed plus 0.15 to the 4th, etc. All right, now this is actually our starting place, right? So this is the series we're looking at right here. So let me call this A, just so I have something to talk about. So here's our A. This is what we're missing from the series we're looking at. So I think the fastest way we could do it is just to subtract this away now. Right? So if I were to move these two over, right, I'd have 0.87, then minus 1, plus 0.15 is approximately, now this 0.15 squared minus 0.15 cubed plus 0.15 to the 4th minus on and on and on. So this is our A. And so you see here we have the value we got from the series minus 1 plus 0.5 will actually equal the series that we're looking for. I think that's possibly the quickest way to do it. There are some others, but I think this is the least complicated way. So really what I would say is it's going to be, I'm going to put this in exactly. So A is going to be, instead of putting the 0.87, I'm going to put the 1 over 1.15 minus 1 plus 0.15. Right, and I'm going to plug that in the calculator directly just to get something. All right, and I'm going to round to, actually, this comes out to be an okay-ish fraction. So let me just give the exact fraction here. This comes out to be 9 over 460, which is approximately 0.0196-ish. Okay. Okay, so this is how you can deal with starting at a different point. Of course, this could be a problem if you're starting at something like 10. You might not want to do that. So let's look at another example like this, and then I'll show you what you can do if you have to, say, start, like doing it this way, but starting at 100 would not be ideal at all. Okay, and I'll show you what you can do in those cases. Okay, so for this next one, there's actually a couple things going on here. One, our starting point is different, right? We're starting at 1. But also, I don't have everything raised to the k. In fact, this is the series as k goes from 1 to infinity. I can actually bring this 4 out and have this be 1 over 12 all to the k. So the 4 is not being raised to the k, while the 12 is. So here our r is actually 1/12, which is less than 1, so that's not a problem, but what do we do with this 4? Well, it turns out that a constant in front of a geometric series actually doesn't keep it from converging. So actually, this series here, if you have a times r to the k, that's going to equal a over 1 minus r if the absolute value of r is strictly less than 1. Okay, so really, if you've got a constant sitting out front, it just sits up top. Okay, you don't really have to mess with it, except the constant just comes along for the ride. Because multiplying by a constant is actually not going to affect whether it converges or not. All right, so it just multiplies it. So that helps, because that means that if we were starting the series from 0, right, 4 times 1/12 raised to the k, I could just say now that this is 4 over 1 minus 1/12. Okay, and then we have something we could actually manipulate. The problem is we're starting at 1, we're not starting at 0. So we'll do what we did last time. Let's manipulate this a little bit. This will be 12 over 12, so this will be 4 over 11 twelfths. So this will be 4 times 12 over 11. All right, which will be 48 elevenths, which isn't the nicest thing in the world, but, you know, it could be worse. All right, now, so here's what I'm going to write. I'm going to say that this series 4 plus 4 times 1/12 plus, I may need some more room here, actually. I'm going to give myself more room. Okay, so 4 plus 4 times a 12th plus 4 times a 12th squared plus 4 times a 12th cubed, on and on and on, we know equals, which we got over here was 48 over 11. All right, but we're starting at 1. So this is the k equals 1 term. This is the k equals 0 term. So this here, from this point onwards, is actually our b. So we need to move this 4 over. Okay, so I'm going to say that, you know, all of this is my b. And I'm going to move the 4 over, so I'll have b is equal to 48 elevenths minus 4. All right, and that will be, shouldn't be too hard. That'll be, whoops, minus, not plus, minus 44 elevenths. So that's going to be 4 elevenths at the end. So b converges to 4 elevenths. All right, so, you know, it's a little tricky, but hopefully not too bad. Okay, so here, as promised, is an example of just, I didn't add in another constant, but this is just a another funky starting place. We're starting all the way at 100. So this is not something where I would want to calculate 100 terms and then subtract them away from what this is going to be. Okay, so here's what we're going to do to help us with this. Well, first of all, we know what our R is. Our R is 2/3. That's going to be less than 1, so we're good with convergence. So if this was greater than 1, it doesn't matter. It diverges. It doesn't matter if it starts at 100 or 1,000,000. It will diverge. Okay? So here's what we're going to do. To help us, we're going to go back to that formula we had for Sn. So remember, Sn was 1 minus r to the n plus 1 all over 1 minus r. Now, if you had a constant in front, you would just have a's up here. Okay? Whatever those constants were. So that's what we're going to look at. So we are looking at our C is going to be 2/3. Well, it starts at 100 and goes from there. Okay, so what we're missing k equals 0 through k equals 99 from the main series, k going from 0 to infinity of 2/3 raised to the k. All right, so we can actually get that with S99. Because what is S99? S99 is going to be 2/3 to the 0 plus 2/3 to the 1 plus 2/3 to the 2 plus 2/3 to the 3 all the way up to 2/3 to the 98 plus 2/3 to the 99. Well, again, this is what we were hoping not to have to calculate. Thankfully, we don't have to, though, because we have this nice little formula here that tells us that s to the 99 will actually be 1 minus 2/3. 2, so keep in mind this is n plus 1, so this will be 1 minus 2/3 to the 100 all over 1 minus 2/3. All right, now this, isn't pretty. However, it's way better than trying to calculate all this by hand. Okay, so let's write a couple things here. So the series k going from 0 to infinity of 2/3 to the k is going to be 1 over 1 minus 2/3. Okay, so that will be 1 over 1/3, because that's 3/3 minus 2/3, which is 3. Okay, well, this series also I could write as the series k going from 0 to infinity of 2/3 raised to the k. I could also write as the sum going from 0 to 99, 2/3 to the k, plus the sum, or the series really, k going from 100 to the infinity. That sort of seems familiar. That's kind of how integrals work, which again, these are interchangeable. Well, not interchangeable, but these are, remember, integrals are series. Okay. So, this we found was 3. This is S 99, not 100, 99. And this is what we're looking for. That's our B. Right? That's, or was it C? That's our C, sorry. That's our C. That's what we're looking for. Okay, so now we just have an equation, right? 3 minus S99 is equal to C, and we found S99. We didn't calculate it, but S99 was this beast right here. All right, so 3 minus S99, which is 1 minus 2/3 to the 100 over 1 minus 2/3. Now what I will do, this is also 1/3, so this ends up being 3 minus, let me put parentheses around this, okay, minus, and this will be 1 minus 2/3 to the 100 all over 1/3. Okay, so I'm going to continue this up here. So I have 3 minus 3 times 1 minus 2/3 to the 100. Now, I will say you can just sort of throw this in your calculator and you'll be fine. I'm just showing what you can do to help simplify it first. And now we can actually factor out this 3 and get 1 minus 2/3 to the 100 is equal to C. So I have 3 times, when we distribute that negative sign, notice the ones are going to cancel and we'll just get 2/3 to the 100. Okay, so if I were to calculate that, I get something very small. I got that C is about 7.37 times 10 to the negative 18. So something very, very small. But think about what we've just done, though. It should be really small because if our original series converges, right, going from 0 up converges to 3, and we've taken away 100 terms from that. Well, remember, these terms have to go to 0 really fast in order for the whole thing to converge. So we took away the early stuff that could potentially be kind of large, and all we're left with are the things that are really, really close to 0, and we're summing those up. Well, we got something really, really, really close to 0. In fact, I did just check plugging it in, just like here, right? Or like right here. I plugged this version in my calculator, and it literally just gave me 0. Okay? So it's not actually equal to 0, but it's something very, 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 very close to 0. All right. So hopefully this is enough to get you all rolling on the homework. Okay. Yeah, so I will catch you all on the next one. Cheers.